Cool. Okay. Yeah, so a little bit about myself. My name is Ayabami Edo, and then I'm a second year PhD student at Electrical and Computer Engineering, University of Florida. And I kind of put my research topics there. It's just for fun. You know, they're pretty long, and I don't intend to say anything about them. Yeah, and then I also work with the Center for African Studies here at the University of Florida. So today, I together with Dr. Nystrom will be anchoring this session. So I'd like him to just briefly introduce himself. Dr. Nystrom.
Hello, everyone. My name is Stephen Nystrom. I'm from Central Ohio, which is in the Midwest of the United States. I did my undergrad at Ohio State University in chemical engineering and physics. And then I just got my PhD from the University of Florida in chemical engineering this December, where I focused on reactor design, chemical reactions, and doing chemical simulations. I had the opportunity, or the situation presented itself both at Ohio State and UF when I joined the labs. I had to build everything from scratch as it was a brand new space. So I got a lot of experience building electronics and hardware and reactors and everything like that. And so I've now been volunteering on this vent project for around 8 to 10 weeks. And yeah, so hopefully we'll be able to inform you all on how we built it and give you guys some good heuristics and possible replacement parts for you guys to make this ventilator in Africa or anywhere else.
Awesome, thank you. Thank you for that. And then also, I like to give credit to whom credit is due. You know, a couple of people are like, hey, did you do this? No, I did not invent this. So this is a work by, primarily by Dr. Samsun Lampotang, who is a professor at anesthesiology, professor of anesthesiology, and then he's the director of CSSALT, which is the Center for Simulation Safety and Advanced Learning Technology. So this webinar, this work is kind of a collaboration with CSSALT and the Center for African Studies, University of Florida, which is headed, the director is Dr. Brenda Chalfin, who is a professor of anthropology. I'm glad that, you know, both of them are joining us today. Yeah, I don't know, Dr. Sam, I don't know if you want to say anything. Is he still there?
Yes, I'm still here. Well, welcome everybody. Thank you for taking time to attend this webinar. I won't say much. We hope we'll be able to help you. And I'll just stay in the background and let Edun and Stephen run the webinar, and I'll answer questions if needed.
Awesome, thank you. Yeah, so this work has been on for quite a while. When the whole COVID-19, you know, started, then there was a quest for, hey, where there's a crisis, shortage of ventilators, we need to also, you know, contribute our quota, which is the idea of this came on. And then ventilators are quite expensive, not easily accessible. And then we thought of you know, together with the team, thought of, can we do something that is quite cheap, you know, easy to get, using homemade materials, and then I see very effective, which is what brought about the pan ventilators that we now have today. And then currently it's been submitted to the FDA for approval. Yeah. So we have volunteers all over the world. Of course, that's why it's open source. Volunteers, that's the map, all over the world, Africa, Asia. And also, if you think that you have something to contribute to it after today's webinar, you know, feel free to reach out to us at Zoom. If there's something that you think, hey, you're doing this, I think we can add it, make this better, make this more sophisticated, or whatever you think is appropriate or you want to contribute, yeah, that's highly welcome. Yeah. Yeah, so the current situation in the world, as some of us might be aware, you will see that these cases are, you know, still kind of growing globally, in America, Europe, and even in Africa. The cases are every day increasing. Yeah. Some of these cases, for example, this is from the World Health Organization. You'll see that the number of cases reported for Africa is about 248,000, which is very different from what the African CDC reported. So quite some disparity, you know. gathering of data and the likes. For example, if you look at African CDC dashboard as at yesterday, when I pulled this up, you see that the World Health Organization says there are 248,000 cases, but the African CDC says there are about 348,000 cases. And of course, this is those that we know, that we are aware of. I mean, just in Africa, focusing that we are aware of. Of course, this is also hinged on the fact that, hey, are we doing enough testing and stuff like that? But based on the report that we have, we see that over 348,000, and then the deaths has risen to about 9,000, which is about 3% of the number of cases that has been reported. So you see that this is a growing concern, and there's something really needs to be done about this. So one of the things that of course could be done, just the ventilator part, which we're going to focus on, and then just looking at the map, try to localize how it's happening in the whole of Africa. You see Africa is badly being hit by the coronavirus, and then you see Egypt. So you have Egypt at the top of there. Egypt is also being affected to a great extent, and then you see Nigeria, and then you see Morocco here, you see Algeria. You see that these cases are increasing and then going beyond hands. And then, okay, so this just also confirms you see the exponential increase, which means as we do more testing, we're beginning to realize more cases as the day goes by. Yeah. And of course, to combat this, the CDC guidelines are there that needs to be followed. But medical supplies are also very, very important, of which one of them is ventilators, because you have a serious situation, admit somebody to the ICU. Of course, you want to have the resources to cater for the person, which ventilators is one of the required things that is needed. But then it is surprising to know that as at April, when this data was gathered about the availability of ventilators in all of Africa, you will see that it's really, really low compared to what you'd expect to have in an ideal setting. For example, look at Somalia. Somalia does not even have any ventilators as at when this data was gathered. I tried to get what the updated data is, but it's not available right now. It turns out that about 10 African nations does not even have a single ventilator, which is a serious issue. So imagine if you have coronavirus case, a very serious case, and then there's not a single ventilator. That's a huge crisis. And then look at DR Congo, for example, there are 5 ventilators in the whole nation, and then that means that about 20 million people would have to share one, right? You have 20 million people per to a ventilator. Mali, Madagascar, South Sudan, Burkina Faso, Burundi, Zimbabwe, and then even in Nigeria, for example, Ethiopia, 557 ventilators. That's about 104,000 people to a single ventilator. So you see that this calls for people coming in from different angles. If you happen to be a business person, it might be an opportunity for you to say, hey, how can I help? If you're an engineering person, hey, can we start building something to assist? And then the good thing is what we have here that we're about to show you was made from home and locally available materials. I think the total cost of everything was beyond about $250, I believe, whereas a standard ventilator is about, you could have it in thousands of dollars, but this, putting all of this together was about $250, which is really, really quite affordable. So you see that this is a very serious situation that despite of our field, in spite of our area of specialization, there's a way that we can actually come into this. So I mentioned Nigeria. So you see Nigeria is about 169. Again, this is as at April. That's about 1 million person to a single ventilator. And then we know that people have been trying to help, like the Jack Ma, trying to send medical supplies, to Africa. But then we as people, I think people there also need to step up to this challenge and then, make these resources, use them, which is why we are offering this webinar to kind of put people through, this is what we did. We could also replicate that there in Africa. So I'm just going to give a brief overview of the whole system. So here you see to the right, this is just what you see the schematic to the right, and to the left, the picture, just a video of the whole system. I'm gonna post this. Just gonna play this. Post it here. So you see the whole thing in a very simple, small box fixed in there, based on this schematic that you have. So what you see here at the top left is just the test log that we use. Of course, you don't want to use this on a human being. So we had the test log to test what we built based on the schematic you see there to the right. So now this is just the box. This is the whole thing. And then in this section down left is the inspiratory section. And then the other, I don't know if you could see my mouse, the cursor. Can we see the mouse? Okay, cool. That's where you have the inspiratory section. So I'll give you a brief overview, at least a high level view, so that, so when we get to the specific details of the engineering parts, you would have learned something along the way. So, so basically we have air coming in, about 50 psi of oxygen coming into the ventilator. You have a pressure regulator in here. So basically what the pressure regulator does is, you just want to, the air, with the knob, you can control what the quantity of oxygen you are supplying to the patient. As you turn the knob, you are controlling the tidal volume. So think of tidal volume as the quantity the amount of air that the person inhales when you breathe. Right? That's the tidal volume, the quantity of air that you kind of inhale when you breathe. Yeah, so that is controlled by the knob. And then what you see there now is we have this three-way solenoid, such that, like a switch, when the air comes in, you have the inspiratory valve, you have the expiratory valve. So you want to, when the air comes in, you want to first of all close the expiratory section, this is the valve, and then you want the air to go in just through the inspiratory valve, which we have on the left. So to the right, what is being touched now, that's the expiratory section of the ventilator. And then to the left, you have the inspiratory section of the ventilator. I keep pressing the wrong thing. Good. So when the air comes in from an external source, it goes through the inspiratory section of the ventilator. So two key things that we included there at that section, two key things. We have the overpressure valve, and then we have the anti-asphyxia valve. So those are just safety measures that we put in there. The essence of the overpressure valve is, of course, you don't want to supply too much pressure. And then you have the anti-asphyxia valve there also. It's also a safety measure, because for any reason, if the device happens to stop working, air is not coming in, you want to make sure that the patient is taking in a fresh air rather than inhaling what has been exhaled before. So the air from there goes through this orifice and then gets to the test lung. In this case, stands or represent the patient. And then we have the control box there, which is like the brain of the whole thing. So think of that as, maybe the CPU of a computer, right? So that has the Arduino, the microcontrollers that kind of control the whole system, which is the main thing here. I think Dr. Nystrom I'll let him talk more about that. And of course, we have the expiratory section of the valve that takes in air from the patient and then to the environment. So now we're going to get to the ventilator design and assembly. I've kind of motivated, the reason why we need to take this serious, the reason why people need to get involved, and then utilize this opportunity to help in one way or the other. Yeah. Dr. Nystrom, do you want to take it from here?
Sure. Share. Cool. So how to find a lot of this documentation is just go to Google and University of Florida open source or OS Vent. And just by doing that, you can get to the website for CSSALT. And build and test instructions is where I have this PDF here. And so basically where we're at the University of Florida is we're kind of doing like 3 different parts of the vent. The one that we're showing you guys is the open source. And so this has in more consideration of trying to make sure that these parts are available for everybody anywhere. We've started making a slight modification for trying to get FDA approval where we're actually using a mechanical valve that controls the pressure of the system. Versus this one that we're using is using an electronic control, but we're afraid that this PEEP valve, the pressure release valve, might not be available in other countries or would very quickly run out. And so we're just going to talk about this open source vent. And so we've kind of talked about it a bit, but here is the inspiratory side. So that's the side that's delivering air to the lungs. This is the expiratory side, and so this is the part that's leaving the lungs. This is the control box, which is hooked up to 2 different motors. These are just solenoid valves, and in this case, we're using them as, these are actually designed to be used in the garden. You would hook this up to your garden hose, and this would be flipped on and off throughout the day to water your garden automatically. And so we have managed to get good enough control to basically get the FDA approval on a ventilator using just these garden sprinkler valves. And we have just this hooked up to 12 volts DC. And so that's kind of just the overall design. And this is just, I guess, a better picture of indicating all that. What we've made it out of is PVC, polyvinyl chloride, as well as CPVC. And the only reason why we have 2 different materials is that, at least when we were buying it here in the United States, the different OD, the outer diameter and the inner diameters for CPVC and PVC are different. And so depending on what we were trying to hook up, like the breathing filter, we needed to use slightly different size tubing that had different internal and outer diameters. So when cutting the PVC, the instructions here are pretty clear on like the sizes of everything. If we look at this picture here, this is all the pieces you need. And all the sizes are there and how to assemble that. So we're not going to belabor too much on that point. But the important thing to know when cutting it is you can cut it almost any way. You can use hand saws, you can use drop saw, you can use PVC, just the PVC pipe cutters. You can use a sawzall or a rotary saw, whatever you want to call it. But it's very important to deburr. No matter what method you use, you're going to have edges that are rough, and we do not want that breathing or getting into the filters and clogging it. So it's really important to get a deburring tool. You can use an X-Acto knife if you're careful, don't slip and slice your finger. But yeah, if you have a deburring tool or sandpaper, what you want to do is like sandpaper it down, get it nice and flat. Because if the piping or tubing is at an angle, when you put it in that fitting, it's not going to have a tight seal, and air has a tendency to leak out, and that would mess up our pressures and our flows. So yeah, make sure you flatten the edge and then deburr it so there's no tools, and also wipe it down with a damp cloth. This will help remove all the excess powder just to make sure we don't clog up the filters, or even worse, get it in the patient's lungs. And here everything is nicely labeled. Like I said, I showed you how to find it. You can just Google University of Florida OS vent and click on the build instruction links. The tools to make all this are very simple. A couple different drill bits. Here we're using inches, which you guys are probably using metric, but you guys can easily figure out conversions. So all you need is a few drill bits. This is super glue or cyanoacrylate. It's just super glue. It hardens very quickly. And once it's cured, it does not really off-gas any dangerous VOC or any dangerous chemicals. So you don't have to worry about that once it's cured. So give it 24 hours after you applied it. And if the patient can breathe with this in the tubing, and no gases, no toxic gases at any significant level will get in their lungs. So this right here is the anti-asphyxia valve. And so the purpose of this is there a completed picture that shows what it looks like at the end? Hang on, I'm just trying to show you the end result so I can explain it a bit better. And so yeah, this is it right here. So what this does is this is attached to the machine. And so essentially what happens if the air line gets cut off to the system and the patient needs to take a breath? Well, we don't want them basically trying to take a breath with no air in the system and then they suffocate. And so this little flap will open, this flap right here is just like rubber. And you might need to put a washer or two on it to get the weight, but basically there's a hole that is drilled inside of this piece of tubing, and that flap will lift up if basically the pressure outside is greater than the pressure inside of the system, it opens. And so if you're trying to breathe in and there's no air in the system, you're creating a vacuum relative to atmosphere, that's going to make this flap lift up, and then this prevents the patient from suffocating. Very important if anything fails. The opposite end of that is an overpressurization. So let's say the expiratory side or some part of the system fails, the house line where all the pressure is coming into the system, that gets a huge charge, something gets messed up. We don't want the patient's lungs expanding rapidly, obviously. And so what we've done is we've devised, using a 3D printer, is a pressure relief valve. And so by twisting down on this threaded fixture right here, you basically condense a spring, and it, if you tighten it all the way down, it takes like, I can't remember the exact unit, but we have it set so that whatever the max pressure the lungs can handle, this thing will fire at that. So the system never will go above what the lungs can actually physically handle, which is also a very important safety feature, because things might go wrong, you know, a tube might get pulled, so electric might go down. And even though that these do have a battery backup, it's great to have these safety features, and I would say they're definitely a must. So how actually to make these, again, all these files for the 3D printed parts are online, as well as the build instructions. If you do not have access to a 3D printer, what you can do is try to find some sort of mechanical pressure relief valve that's already sold at Swagelok or your local hardware stores. I really don't know the supplies or what you guys have access to in the various places all around Africa. So basically you need something to prevent the patient from asphyxiating, you know, suffocating. So something that will open when the pressure inside the system is less than atmospheric, as well as another part to basically make sure the system does not overpressurize. So this is more the FDA approval, and this is what we're demonstrating, but those are the phenomenons you need to make sure that the patient cannot asphyxiate, or that their lungs basically cannot explode from too much pressure. So you need to come up with valves that operate within those pressure ranges. We use these rubber, or I think this is actually silicone, but basically a rubber type mat that we put at the ends of these stoppers, and these act as gaskets. This plastic on silicone rubber seal is fairly tight for what we're doing, and we don't really notice any leaking. And here we're also using super glue, because once it cures, it's really strong, and we don't have to worry about any bad gases. This is just more about the overpressurization valve and how to explicitly assemble it. But basically, it's just a valve that when the pressure inside the system is larger than outside with that spring, it opens up and lets the system vent. This is actually one of the most important pieces, is we're all using basically 1/2 inch, 1 inch, or 3/4 inch PVC piping. But if we just had 50 PSI, I don't know what that would be in whatever units you guys are using, but if we had 50 PSI, and we just open up that sprinkler valve even for a 1/2 second and closed it, that amount of air rushing through that surface area pipe would, again, just be way too much. And so we actually have to design an orifice. If we look very closely, you can see that there is a very, very small hole. Now this orifice is made of, I think this one's made of PVC, or this is made of something, but regardless, you need something in there that will block the tube primarily, and we're using a 0.052 inch drill bit, or a number 55 drill bit. So this is an extremely small hole. So the house air pressure is at 50 PSI, the sprinkler opens and lets the air in, but then very next thing it encounters is this orifice plate, and that reduces the flow dramatically. So you basically have a lot better control on the air going into the lungs, and have better control on using the sensors to read that and everything like that. So overall, now this kind of makes up the entire inspiratory, or the inhaling side of the breathing apparatus. We have house air coming into a filter, into the orifice, anti-asphyxia and overpressure valves. And then this now hooks up to the wide piece that will deliver the air to the lungs. And this right here is a pressure valve. This is something that actually might be an issue for Africa, because I know India was having this issue. In the United States, basically all of our hospitals have a house pressure line. So basically all the rooms have a little metal apparatus where you just hook up a hose to it and you get 50 PSI, 40 PSI, whatever they have set that hospital, and it's always there. I know some of the places in India actually did not have hospital lines. And so basically they needed a way to get pressure. And so you could use a normal air compressor, but there's going to be metal chunks and probably stuff you don't necessarily want in that air compressor going into lungs. So you have to filter that. I know what they were doing in Africa, in India, was actually trying to convert vacuum cleaners. So then once the vacuum cleaner sucks it in, you tweak the turbine so it delivers that into a vessel and you actually pressurize it. So they were trying to basically get a continuous pressure system using vacuum cleaners. The links might be on the website, but you need to somehow obviously generate a constant pressure. So however you guys need to go about doing that, that's crucial. But here we have a house line, and so we have a pressure regulator to step it down. And this controls the tidal volume, which is how much air we allow in the lungs every breath. We'll get more into that in a second. Again, here's just a solenoid valve. We hook up to 12 volts. Any metal on metal or plastic on plastic or plastic on metal threading, we use Teflon tape, and this is just to make sure we have good air seal as well. So we have good control of our pressures and flows. Again, basically every thread you need to put on Teflon tape. That's just good engineering practices. And then we use Tygon tubing, typically 1/4 inch, to connect the various parts from the inlet pressure into the inspiratory side, into the solenoid valve, which controls the expiratory valve. So yeah, we just use Tygon tubing, and all the links for this setup are in this documentation. Scrolling down. Yep, here's that orifice again. This is just going into more detail on how to design it. You can see once we put it in there, we actually put an O-ring in there. And then when we put that next tube tight up in there, it compresses it all. And then we only let air flow through a 0.05 inch hole versus the 1/2 inch or 1/4 inch or whatever it is. The other thing that's important to make sure we have a good air seal is that we're using, here, let me zoom in on this so people can see a little bit better. We're using Loctite silicone sealant. And so this is often used in aquariums or fish tanks or glass on glass or plastic on plastic. It's waterproof. And once it has cured, it has no bad off gases. It smells pretty bad when you first put it on. But again, after that first 24 hours, there's nothing dangerous in those fumes anymore, at least at a level that would cause damage. So on basically every single PVC fitting that we use, we put the silicone sealant on. So I typically just, you should use a glove. However, if the glove is not the perfect size, it's actually kind of hard to work with. So I'll sometimes just use my finger, but you just wrap it a really thin layer around the outside of the tube. And then when you put it inside the fitting, you twist it, rotate it, and then push it in really tight. And this takes, I think, a couple hours to completely cure inside that area. But this makes sure, again, that we don't have air leaking out. And the other thing that this does is that when we don't do this, and if someone were to bump the ventilator or drop something on this ventilator or kick the ventilator or something, we don't want any of those connections coming loose. Worst case scenario, the PVC in those fittings pop completely out, in which case the ventilator is completely useless, and that could definitely kill a patient. And so we noticed that we had to do a drop test for the FDA where we took 1/2 kilogram steel ball and dropped it like 5 feet high onto this. And the first time we did that, the tubing and the fittings popped out from each other. And so once we sealed it up, how we're demonstrating here, the PVC fittings did not pop out when we dropped a 1/2 kilogram steel ball on it from 5 feet or about 2 meters high. So this is important for air sealing as well as a safety feature to prevent the system from popping out or anything like that when it's actually in use. To make sure, we drill a single hole in the PVC here. All the other PVC, we just simply use that sealant and push it in. But with the orifice, because we have a large opening going to a very small opening, that pressure gradient could actually push that PVC out. because you have that orifice sitting in there, and then it just will push it out because that hole is so small. So here we actually screwed in. This is the orifice would basically be right here. Here's that O-ring, and then this is pushed up against it. And so we drilled this piece in to make sure that, you know, when we're going down from 30 PSI into this little tiny hole, that we don't fire that tubing out. And we didn't have any issues, but this is just a precaution. And again, anytime we drill a hole, make sure you deburr it really well, remove all those shavings. We don't want that clogging up filters or getting in patients' lungs. This is just showing how we would screw that in and putting on the other fittings. Yeah, that's basically that one. Here's us using more sealant. Sealant on everything. And okay, now we're getting to the expiratory side. So what we've covered now is the air's coming in from either a pressurized vessel, the house line inside the hospital. It's going through a valve. It's going through, you know, the sprinkler valve, and now that's going into the lungs. Once it goes into the lungs, it comes out and goes through this expiratory side. And here we have set up a flow meter, basically. And so what we have here is we hook up one part of a sensor to this rod here and this rod here. Now, these distances between this, as well as these cross-sectional areas, are very important because the driving force, like how you determine flow, is the driving force. It's the difference in pressure. So if you have greater pressure on one side than another, that's how flow occurs. That's why water flows down rivers. That's how we actually exhale and inhale. Their diaphragm expands our lungs. This creates a vacuum, and this expands that pressure, or expands the volume. The same amount of air is in our lungs. And so with that expansion, now the pressure in our lungs is less than outside. And so since the pressure outside is greater, it forces air into our lungs. And now when we exhale, we either push up on the diaphragm or just simply relax, and this closes that volume in our lungs. We have the same amount of air inside of our lungs, but so the pressure increases. Well, now the pressure is greater than atmospheric, and so we actually exhale. And so by controlling the volume of our lungs, this changes the pressure, this changes the driving force of whether we exhale or inhale. Well, same with this. If we can measure basically the pressure difference between 2 points, and we know how far those distances are apart, we know what the material is, it's air, so we know its viscosity and all those properties, you can actually very easily, to a certain degree, to a very fairly certain degree of measurement, you can measure the flow. And so this is how we measure the flow. Again, very simple materials: super glue, sealant, and a few drill bits. And marker to label everything, because that makes it easy when you assemble it. However, these brass rods that we're using, they're very small. I think they're like an 1/8 inch OD, outer diameter. And so when we cut them, if you just use like a pair of snippers or even just a Dremel, it compresses that hole, and now we don't have that diameter that we need. And so when we first cut it, and then basically you have to take a Dremel or a sandpaper and trim off the edges and get it deburred, and so that the hole is very, like, there's no deviation in that hole size. And so you hold up to the light basically, and if you see it looks like a good circle, you're good. If you see any bars or burrs in there, you got to keep deburring it. The links and all that are in there. This is also important, is the depth. So we went when we put these brass rods in here, you see that we want the inlet to be right in the center of the tube. The placement of this is important because the flow rates, the boundary layers, and the pressures actually are different if you measure it up here versus down here. And so making sure we get the center here is important. And then we super glue it because we don't want it to move at all, because we'll be taking tubing and pulling it off and on. So you don't want that tube coming out. You don't want that placement to get shoved down to the bottom of the tube or move up to the top. So we super glue it. And do not use your hand or finger to push that brass rod into this. This hole right here is a very tight fit. Use a hammer or something like that, because if you use your hand, you actually slice your hand open. I did it twice. So use a metal or blunt object to push that in there a bit, but make sure you don't collapse the hole. It's probably a good idea on some of these pieces to clamp it while it dries. And again, we're just using that Loctite silicone sealant. Yeah, and so this is just showing you what we're using here. So this is available at our local, we would call them, at our local like hardware store, Home Depot, Lowe's. This you can just buy off the shelf. These are the valves that we're using. They're just made for the garden, but they're working just fine. So the inspiratory and the expiratory valves are working differently. On the inspiratory side, it's being controlled electronically. So we send 12 volts, and this opens the valve basically that allows the air through. However, this is kind of slow acting and very on-off. We either apply 12 volts or we don't. That valve is either open or closed, and we have a little bit of that time in the transition. But basically, the valve is open or closed, and it takes a 1/10 to a 1/4 of a second to do those changes. So it's very slow. On the expiratory side, we need more control because we want to basically stop the exhale exactly when we want to, when the pressures are stabilized, when the flows are right. So we needed more control on the expiratory side. And so what we did with that valve is we're not actually using the electronic controlled solenoid valve that comes in there. What we did is we hooked up an air line to, I know I'm deviating a bit, but it makes sense. So we basically hooked up this air line to the valve here. This is where we're going to hook it up right here. And so instead of using this electronic controller, we're using this air valve, and this air valve is controlled by this clipper 3-way valve. So essentially one side is always open to the sprinkler here. And then the other side of the valve is either open to that house pressure, 30 or 50 PSI, or vent. And so by sending an electrical impulse to this 3-way switching valve, we can actually very quickly toggle the valve back and forth, basically letting the valve here vent or gain pressure very precisely, very rapidly. We can do a few toggles. And what that does is it allows us to more slowly approach we can have a more control over opening and closing. It's not on off. We have a little bit more control on where that position is, and we have a little bit better control on timing by using this 3-way valve. I'll show you a little bit more pictures with that in a second. But since we're not using this electronic part anymore, what happens is the diaphragm, and we can kind of talk about how the sprinkler works, is this spring is pushing against the diaphragm in here. And so when the solenoid gets 12 volts, typically it pushes a magnet down. This magnet then basically opens and closes the diaphragm, which allows flow in and out. However, because we're now using air pressure versus the solenoid valve, we noticed that when we pressurize the top of the dome, we actually got air leaking into the system because the sealing around the O-rings on this tube right here, this is where the air is flowing down here if you see like this little cavity. But basically the air on the upside of the diaphragm would be able to leak down into the bottom side of the diaphragm. So now what we were trying to use to close the expiratory side would actually be forcing air into the expiratory side. And so you needed to devise, if you're using these valves, we needed to devise a slight little, basically bushel, like a little, spacer, and we put an O-ring on top of that so that now when the air pressure closes that diaphragm, there's no air leaking in. This is very dependent on this exact valve. If we use a different type of sprinkler valve, we might not have had this problem, or we might have needed a different fix. So you just have to pay attention and think about, is there any way that we're leaking additional air in or out of our system at the valves or any of our fittings? So that's all this is getting at here. That's that spring I was saying, that's what helps. Yeah, the spring pushes up on the diaphragm. So when that magnet gets 12 volts, that magnet pushes down and it closes that. And then this here is a filter. And so our Y pieces, that's like the tube that goes to the trach, and then one's inspiratory, one's expiratory that goes to the ventilator. These will have filters. And so it's kind of like, I can't remember the exact term. I'm a chemical engineer, not a medical person, but this is basically like a HEPA filter. It just filters out. I think it grabs humidity as well as, filters out particulates. And so we like having these on the expiratory side. First off, this acts as a resistor, so it helps slow down the flow a bit. It's kind of like putting an orifice in. By having more resistance when something's leaving, it reduces that flow, so it's not as on off. Like when you exhale, it's a little bit more slow because it has to go through this resistive part here. But also what it does is it prevents people from exhaling the virus or COVID straight into the atmosphere. So making sure you have a filter on the expiratory side would probably be good to help prevent spread. This is not based off any medical journals. This is just me thinking if you're constantly exhaling through a machine, that particulate will go to the atmosphere. So we should have a filter. This is what I was saying about how we're not using the electronic solenoid. We're using an air pressure line. So we have some Tygon tubing. We push it in this hole here. It's a tight fit, so you kind of have to like twist it in there and work with that. It might take a minute or two. But once you get that in there tight, you use a lot of, we used epoxy, not even super glue. So we use epoxy. This is outside of the system. You don't have to worry about off-gassing or any of those fumes getting inside the person or damaging them. And epoxy is stronger, at least this one is. So we made a 2-part epoxy. It looks like, yeah, we used a 2-part epoxy, and then we just made that fitting very strong. So this connects to the control box. This basically gets 12 volts sent to the inspiratory valve, or 12 volts sent to the switching valve that goes to the expiratory side. This is just showing the box. This is the clipper valve that we used. I can zoom in on this a bit, but depending upon the availability of supplies in your region, what you have access to, this is obviously something that you probably not use this exact part. It might have a different voltage, might have a different current, probably different timing. But the phenomena you want to do is basically control the expiratory side as well as you can. And so we wanted to use air pressure, and this 3-way valve allows us to like get a better control of the expiratory pressure. And again, we use Tygon or the Teflon tape on all the fittings. Some of this is soldering. We put these pieces in. Some of them we screwed in. Some of them we soldered. I'll get more into the controls and the electronics in a second. So these are called plenums, or that's what we're calling them. And so what this ends up being is basically just a dead space. And so we have tubing running from that flow sensor, as well as another part, we have a pressure line that runs into our system so we can read the pressure of the lungs. This is located right at that Y piece. So we basically see the pressure right at the lungs. And this runs in a thin tube that goes to our system. However, we notice that in these thin tubes, basically the curvature of the tube can make the air be jagged around the edge if you really think about fluid dynamics. If there's any abrasions, this creates eddy currents and convection currents, creates chaos. And so this creates frequencies. And so if you're trying to read the pressure or read the flow, and you have these quick jostle and oscillations, this throws off signaling. If you ever try to do any type of signal analysis, you need to try to remove noise. And so what this is doing is acting as a mechanical filter. And so by having this dead space, basically these super fast oscillations that are caused from various parts, like the air just simply moving along the edge, it going through spirals, it going into new voids, these fast oscillations cause issues. And we can do digital signal, augmentation, and we do to help smooth that out and average. But by having this dead space, those fast oscillations reach this volume and basically get dampened out. And then the pressure continues. So we have to use plenums on all of our lines on the pressure line and our flow lines. And then what this does is, like I said, it acts as a mechanical filter for high frequencies. This is just how to make them. This will these may or may not be needed. Most likely they will be, but depending upon the sensors you use, this could change. But for all of our testing with the sensors we use, with the setup we used, we basically needed these plenums, or else our pressure would not stabilize because it would be way too noisy. So mechanically dampening different signals is crucial. And we use 2 different size plenums. The size of the plenum also mattered greatly. So that might be something you have to play with your model, is you might have to use a longer piece. You might have to use a larger diameter. You might have to change the volume a bit and play around with that. So that's going to depend upon your exact setup with sensors you're using. And this is for the large plenum. It's the same idea, just using the larger size. And I have 9 more minutes, and that should be perfect. So this is what what was referred to earlier as the brains. So this is the control box. This is what I spent most of my time working on. But a lot of the stuff you basically order, there are designs, if you look, those are drilling designs, but regardless, there are designs online that basically you can order these circuit boards already populated. Like we have like all the designs for the circuit boards already be populated and everything. So you can just order that from a company like JC. There's plenty of websites that will make and deliver these in a matter of a week or two, sometimes days, depending upon where they're located. And so we've done almost all the work already in creating the circuit boards, knowing what components go in there. And so you would probably just order it already made. It's cheaper to order all the parts separate and compile it yourself, but that takes hours to solder it. You have to know what you're doing and you're gonna have troubleshooting. So probably buying these boards pre-populated or trying to work with someone who can order all these parts in bulk. If there's a company or electronics store locally or something like that, and they can just order all these parts, to build 100 of these or 1,000 of these, and they just, have people soldering all day once they figure out what they're doing, that also works too. We used what we're calling here a hobby box. It's just a plastic, I guess we don't have a good picture yet, but it's just literally a plastic box that the lid typically comes off. These are used for utility or hobby, a lot of things. So what we needed to do though was basically make spaces for the LCD screen, the liquid crystal display, as well as 4 buttons. And then we needed power in and power out to go to the motors. And so this is thicker plastic. So what we did is basically you drill like 50 drills. You use a small drill bit and you just go around and basically make a perforation, and then you can punch that through and then file it down. And so if you need to make squares and you don't have a Dremel, you don't have a CNC machine, get an X-Acto knife, trace out your square or your rectangle, and then take a drill and just go to town on that and punch it out and then file it. We made these buttonholes just using a drill. Again, you could use an X-Acto knife if you're careful. You're probably gonna cut yourself a few times. Everything's a pretty snug fit here, so we need to deburr everything. And this box has everything labeled. So here we have the LCD screen. We put a piece of acrylic over top to make this watertight or water resistant. I'm sure if you actually submerge it in a bathtub, water would leak in, but if you spill water on top, it's fine. And what's important in both the tub itself that we're using, this big plastic crate that you would store stuff in, is whatever material you use to make the box or this control box, the big box that holds the ventilator or this control box, is it should be not porous. You should not have water soak in. And the reason for that is for sanitation purposes. Because this is going to be used in hospitals with people with infectious diseases, being able to wipe down these surfaces and thoroughly clean them quickly and efficiently is very important. So using a hard plastic, using metal would work very well. We were at a time working with potentially trying to get a contract with the US military to make these ventilators. And they were thinking about using metal ammo crates, what you would put the ammunitions in as their box instead of a plastic Tupperware so that theirs could be more durable. But regardless what casing you use, make sure you can clean it easily, spray disinfectant on it, use wipes, sanitizing wipes, anything like that. And so this should be water resistant so that you can sanitize it easy. If it's not, you're gonna have alcohol, solvents, water dripping on components, and that could short it out. Here we have our buttons. Here we have power in and out. On the back here, we had to put spacers for our PCBs. Our printed circuit boards. So this is what is used for the transducers. We have, overall, we have 2 pressure sensors. We glue the other one here. And what one pressure sensor does is measures the ambient pressure and temperature. Because we're always exhaling and inhaling from atmosphere, in this case, we're actually inhaling from a pressurized 50 PSI, but we're still exhaling to atmosphere. As the barometric pressure and humidity and temperature changes, that actually affects the driving force slightly. And so what we needed to do was use an ambient temperature and pressure sensor, as well as one that I said, again, it runs basically to that trach piece right here. So there's a small little Tygon or medical tubing that runs to the device that's basically right here when you're intubated. And that tells you the pressure of the lungs. And then we also have our flow sensor. And so there's different forms, but basically what it is there's a diaphragm. and it has a magnet with a sensor that basically changes its voltage if it's closed. So one side of that tubing, that the flow sensor had one side hooked up to one part of the tube, and maybe about 6 inches later, there was another one. And so there's gonna be a pressure gradient. If the pressure is greater on one side, that pushes that diaphragm closer, that magnet gets closer to that sensor, the voltage goes up. If the pressure on this side increases, it does that. And so our flow sensor basically has a diaphragm that changes, and this changes the voltage, and we can measure flow rates and do calibrations. So that's what this board does here. This takes the power in from the battery as well as the house, the main voltage in the hospitals or whatever. In America, at UF, we use 110 volts and 50 amps typically at almost all the University of Florida facilities. So just keep that in mind. So yeah, we have our battery, and you can either put 17 volts in if that's the power supply you're using, it's 17 volts, or if you have something that's more like the 13 volts, you solder it in different places. And this is it pre-populated. So this is the board right here that you would probably just order. The pressure sensor needs, can I zoom in? Yeah, so what the pressure sensors are is it's using this little chip right here. Is called a Bosch BMP 280. Barometric, it measures temperature and pressure. That's this little guy right here. And this whole thing is a breakout board for it. Basically, this makes sure that you don't apply the wrong voltage. This has reading stuff that allows you to communicate with I2C, or there's other communications, but this allows us to communicate with this device in a very easy manner using wires, so we don't have to do much soldering. However, this hole right here is what we need to use the pressure. So for the ambient pressure sensor, this is fine. We want it to be exposed to the atmosphere. But when we want to measure the pressure, we actually need to put a plastic nipple on there. Yeah, right here. And so, yeah, we need to put a nipple on here that will allow us to connect a tube to it. And so we very carefully and systematically, you just place that over the sensor like so. And then you very, very, very carefully super glue it. You can get any one, or epoxy, sorry. You can get any of these components right here covered in epoxy. It doesn't matter. You can cover them in whatever. This is using low enough power that there's not going to be a heat issue. You're not going to damage any circuitry. You put that epoxy or super glue anywhere out here. If that glue touches this sensor, or more importantly, gets in that hole, it's done. That sensor is no longer useful. You have to throw away this chip. So apply a lot of pressure to the nipple in the circuit board, apply your glue, hold it, make sure it's secured, and then let it go. Again, if anything gets on the sensor or that hole, it's screwed, so make sure you only get epoxy on every other part of the board. And that's demonstrated, no, not there yet, right here. Boom, and you see all the components are covered, it's fine, don't worry about it. This is the part that you will have to do yourself. You will not be able to order a nipple attached to a BMP 280 breakout board online. So this is something you will have to do yourself. And this is a critical stage. If you mess that up, that sensor's done. That is about a $10 sensor right there. The flow sensor is about a $60 sensor that we're using. So that's the one you do not want to break, is that flow sensor. That is $60, 60, American. Again, depending on the exact sensors you use, your wiring is going to be different. Even the ground and voltage can be flipped depending upon your device. What you use for the clock and communication can be switched. The important thing is that whatever sensors you do end up using, you make sure you know how to communicate with them to I2C and get it working with the Arduino. This is the flow sensor that I'm talking about. So here we have flow from one part of the tube, the other part of the tube. And then inside there's the diaphragm that moves up and down, and it reads the voltage. And then this is like voltage, ground, and then clock and communication. So this is how it sends its information to the Arduino for it to read the flow. And this is just how we set it up. We had to glue some stuff. The board could be revised more. I think we are working on new revisions, but that is that. And now we have a couple of different boards. This holds the buttons, sends the power out, as well as has the screen. There are several different versions of this board right now. So follow the instructions on whatever board you guys get. This is that transducer board all wired up. And then now here is this is the brains of it. Here's the Arduino. The Arduino is doing basically everything on here. We have, you know, a couple other passive components like resistors and capacitors to help regulate and do frequencies, as well as send power out and give power to the screen. And you see here, we use some jack stands. This is going to be completely dependent on the box you use and the exact boards you use. So I'm not going to belabor on how you should assemble this. Plastic or metal jack stands work great. You can see here, it's starting to get a little bit more complicated as we add the other board. And now we add the screen. And then we add a buzzard. And so this is how it beeps at you. You know, that very awesome hospital beeping noise. I think it's called beeping amnesia or whatever, when there's so many tones in the hospital that you just become like immune to them. But regardless, we have a speaker and a buzzer on here to alert people if something is wrong. Here's our screen with our controls. And then we put our plenums inside of the control box. So you see here, we super glue them in. Remember, the plenums act as high frequency filters. So with the air oscillation doing this becomes dampened, and then we get really good average flow measurements. And we put this on the lid, so everything's self-contained on the lid. It makes it super easy. We have to obviously connect using tubing, the plenums to the sensors, as well as the plenums then to the machine. And like I said here, whatever kind of box you want to use, I recommend something sturdy that can have a lid so you don't drop stuff in there, and it's easily cleanable. And I think this is basically summing it up. I just want to make sure I'm not missing anything. It is important, at least if you're using our code with our sensors and our setup, that you really cannot mix up the upstream and downstream when you're measuring the flow. Because basically, if you switch the flow, that changes the direction. So if I put this tube here and this tube here, and then I start measuring, it's going to give me a negative flow rate because I just switched it all up. And we use negative flow rates to actually indicate like an alarm. So it's very important that you do not mix up the upstream and downstream on the expository side when going to the flow sensor. Basically, when you're doing testing, you hook it up. If it reads 0 flow, you switch it, you turn it back on, it reads a flow. If that doesn't fix it, you have messed something else up. What I highly recommend is getting a battery and putting it in here. I don't know how well the power is regulated over in the various parts of Africa, but if you're gonna have any power fluctuations, or even someone accidentally trips over a wire and plugs it from the wall, this battery picks up instantaneously, and it's always being charged when it's plugged into the wall. We have a trickle charger on the printed circuit board, so it's always being charged when it's plugged into the wall. But if you lose power from the wall, if the hospital loses power, if a circuit breaker fails, whatever reason, this battery will kick in, and it should last for 8 to 12 hours, depending upon the current draw from everything that you have around you. Your lid is going to depend upon your setup. And then we wanted to make everything water resistant from the outside. And so all of our holes on the outside, we put silicone sealant, as well as put foil tape. We use zip ties to fix the valves and the PVC to the box. You see here, we just drilled holes in the box, put the zip ties in, and then we covered this with aluminum flashing tape. Aluminum waterproofing tape. You could use this outside or on ductwork, like your HVAC system, your AC or heating systems, but basically just waterproof tape. That is the quick and dirty and how we make it. Like I said, all the instructions and everything is on the CSSALT website here. That is from the University of Florida. So if you just Google this, it will come up. It will come up very easily on a Google search. So with that, I would like to hand it back over to Awambi, and I think we're probably going to start fielding questions. Thank you so much for your time.
Yeah. So I think that's just the basic overview of building the ventilator. But I need to make a couple of notes. So as I was talking, you will see that there are a couple of labelings, the PVPN229, different labeling. So those just kind of make a reference to the bill of materials. So we have a bill of materials on the website that is showed. So because we just want to make everything kind of pictures, make it look nice and fancy, so you don't have to deal with a lot of details on the slides. So those are just annotations that you could reference. And I think I could just pull the Excel sheet up. Okay, yep. So we have this Excel sheet on the website also that just kind of make a reference to the materials that we used. And of course, depending on whatever you have in your local environment, you could use a substitute for any of those. I just wanted to make that note. And then, as I think now we can take questions if you have any question, or maybe you're working on a ventilator already from your hand, and then you probably want to share something. That's fine. And then we're going to send a survey that would like you to please fill at the end of this. So I think now we could just open it up for questions if anybody has questions. So feel free to unmute yourself and ask your question or contribution or whatever. Okay, so I sent a question privately, and then the question is, Dr. Nystrom mentioned putting a filter on the expiratory side. Does the inspiratory side need a filter as well? Avoid breathing in contaminated air.
Yeah, so actually, if you could scroll up a few on your slides to basically the first slide that has like the good picture on the top view. Cool. So on the inspiratory side in this picture, you do not see a filter. However, at that Y piece, I don't think we actually have a great picture of the whole setup, maybe in the video, but basically that Y piece, it's a tube that runs one to the inspiratory side, one to the expiratory side, and then it has a hole here that goes to that trach piece inside, your lungs. Right here, there is a filter, basically leading right between the Y piece and the trach tube. There's a filter or somewhere right along there. Sim could obviously comment better on that exact location.
Edwin, go to the picture of the test lung, please. I think there's a picture of the test lung further up.
I have it in the video.
Oh, you have it in the video. Okay. Yeah. Go to the, go to the video.
Okay,
and,
there.
Yeah, and then unfortunately, so actually zoom in on the flow diagram. The diagram to the right. So there's the filter right there. Can you point to the filter right above the patient, where it says patient? Right there. So that's the filter that you would use on the inspiratory side. But it's outside the box, it's on the breathing circuit, right before the gas goes into the patient.
Yeah, awesome. Okay, different question. Someone said, what is the estimated cost of production and lifespan of the product?
The specified lifespan is 3 weeks, but we have had some ventilators work for 2 months now. But in general, a COVID patient will only need it for up to 3 weeks. It is not meant to be reused. The cost in the United States is about $400, but that's not including labor. But it was also in buying it in one at a time. If you buy a lot of the parts together, you will probably get a discount.
Awesome, thank you. So another question. So I need to make a note though again that we actually get the presentation on the pictures. Then we also have videos of each step along the way. While we're making this, we actually took a video of each step. So if anyone is interested, we could also share that. So you could also watch along with the slides, but I think the slides are very, very explanatory. A question here says, What are post-disinfection measures for the ventilators? Can the materials be autoclaved, and do you have to decouple any of the structures for cleaning?
Yeah, so this is currently designed for single use. The only thing that's reused is the controller box, which maybe you can point if you zoom out. The controller box is what's in. Edwin, could you show the controller box again in the plastic box? So that controller box is reused. Everything else is not reused. However, if you're really running out of ventilators and you can find a way to sterilize it safely, yeah. So that gray box is reused, but everything else in the United States, we plan to throw it away.
So just to comment on stuff that could work, all the gaskets and the salt and the PVC, as well as the sealant, can all withstand alcohol. And so what I was thinking is, like, for the FDA in the United States, this is the PVC we throw. Nice. However, if we need to keep using it, there's no reason, in my opinion, that you just can't flush liquid like the 70% isopropyl alcohol through that PVC and let it sit there for a minute and flush it out that way. Because the PVC is waterproof, all the gaskets and everything should be able to handle alcohol without degrading. And so I don't see any reason why you could not just flush alcohol through the sprinkler system, through the valves, through the PVC and everything, and completely sanitize it. Again, that's not my medical advice. I'm a chemical engineer, but all these components can handle alcohol just fine. So there is that.
Thank you. I think we have a different question here. It says, I want the type of valves used to control the tidal volume and pressure of air that will be supplied to the patient.
Yeah, I'll take that one. So the tidal volume is controlled by turning the pressure regulator knob and reading the tidal volume displayed on the user interface. And that's what the flow meter is for. So you will not get the tidal volume to where it needs to be in one setting like a traditional ventilator, because this is a less expensive ventilator. You will slowly turn your pressure regulator knob and you will look at what is the tidal volume. Let's say you want 500, you're going to see maybe 350. Then you keep increasing on the next breath the pressure by turning the pressure regulator knob. Then maybe you see 400, and you keep doing that until finally the measured volume is 500 milliliters plus or minus 10%. So like 450 to 550.
Awesome. So someone asked about the slides. So I think we showed earlier on how to get the slides. So we have them on the website. I can show it again. Just
yeah, and I just saw a chat. The answer is yes. The pressure regulator is used to control the amount of gas, which is the volume that goes in the lung for each breath, and then indirectly, then it controls the pressure, because the more gas you put in the lung, the more pressure you have. But it also depends on your patient. If the patient has a stiffer lung, for the same amount of gas you put in a stiffer lung, you'll get a higher pressure.
Thank you. Okay, Aliu raised his hand. So you could ask your question.
All right, thank you. The reason I'm asking this one was, it was one of the challenges that we have been facing while we're trying to develop our, ventilator out here. And thank you for, the good explanations.
Oh, you're welcome.
You're welcome.
Awesome, thank you. So I sent the link to the slides and everything on the chat. It says, how long does it take to produce a ventilator? I think I can answer that. So it depends on the kind of, expertise you have around, but if you have people who could really study the slides we have, something you could probably do in a day or maybe two, if you have all of your materials, I think Dr. Nestor, we've worked on it, and in 4 hours, 6 hours, you could get it done. As long
I
as
mean,
you
once you know what you're doing, I mean, you can knock out more than one ventilator a day. It's the hardest part is the most time is spent on soldering, honestly. So if you already have the circuit boards printed and we have a better board, we're working on a single board. If right now you saw we had two and then a screen, we're working on one single design that's being fleshed out with other people, and that's not a part of the current build of the open source. But that is what takes a long time, running all those wires to each other and like setting it up, like making all these fixtures, like putting the buttons on, putting the lid on, hooking up the plenums. The control box takes probably the most amount of time. Cutting all that PVC and deburring, if you do it in bulk, if you just have, I need 3-inch pieces, 5 7-inch pieces, if you just do that, it takes no time to cut. It takes no time to deburr. It takes maybe an hour to glue everything together. So you can honestly knock this out in just a matter of a few hours, depending upon the amount of work you have to do in the control box. The control box is the most time-sensitive part.
So also, please, we sent out a survey. I think if you could please fill out the survey. Do we have any other question? So like we said, if you look at the control board, you see the PCB. So that also takes that you could either get a board that has all of the components on it, or you could decide, okay, I want to buy the components, fix that myself again. That also takes time. Any other question, or maybe you're building something, you have a contribution you want to make?
And any deviation from this build is going to probably require tweaks in the code. The pressure sensors, the flow sensor, all have some sort of calibration or have some sort of communication or address. Like there's a unique address to call every device using this I2C protocol, which is just how it communicates. It doesn't matter the details. But if you get a different sensor, you're gonna have to figure out where in the code to change the address. This might have different resolution. This might affect the timing of stuff. So any deviation from this, especially with the electronics, is probably going to require some revamping of the code. I believe the code is available right now online. We're trying to make it more readable and come up with, I'm actually off the project now. I'm moving to New York tomorrow. So I'm basically leaving this project now. But the other people, they're probably gonna try to make the code more readable and come up with tutorials and stuff for the code. But again, anything you tweak on here, if you use a different sprinkler system, or a different valve, this could cause changes in the code because the timing of that valve is different. So you're going to have to do a lot of quality assurance testing, even with using this setup, just to make sure you're not going to endanger any patient.
Yeah, thank you. So again, we have quite a number of resources. We have the slides detailing the steps. We have the bill of materials. We also have the code on GitHub, if you're familiar with that. So everything that is actually needed for this might just require some modification. So we have them available. If anyone is interested, we can always send that out.
I want to add two quick remarks. First of all, good luck, Stephen, on your move tomorrow. And Eden and Stephen, good job in your presentation. I have two clinical remarks to make. One is the ventilator provides PEEP. So I believe if you're the people attending are building their own designs of ventilators, which we fully support, you need to have PEEP for COVID patients. So make sure whatever design you use, whether it's ours or yours, that there is PEEP. PEEP stands for positive and expiratory pressure. And the second element that we think is helpful in our design and is helpful for ARDS patients. ARDS stands for acute respiratory syndrome. Is that you need to have an inspiratory pause. So when you're putting gas into the lungs, in the traditional way, you put gas into the lungs and then you stop and then the patient exhales immediately. With a pause, you push gas into the lungs and then you on purpose, don't let the patient exhale, but don't push gas anymore. And therefore the pressure can stabilize, and that allows the clinician to make some essentially measurements of the lung characteristics to determine how to ventilate the patient going forward.
Yeah.
That's the two features I wanted to mention in addition.
Yeah, thank you. Thank you for that. So think of PEEP as, the pressure that you have in the lungs. That's, the pressure above atmospheric pressure that you have in the lungs at the end of a respiration, of an expiration. Okay, question says, I'm watching from Nigeria, but I don't think we do have enough capabilities to design a ventilator in a large quantity. What can your team advise? So I think that would depend on, looking at the bill of materials, looking at what we have and what we don't have, or what is in Nigeria and what is not. Depending on that, then, there could either be, if it's required to maybe send some things down there, or if it's a way to source, a sort of, I don't know, maybe funding grant or something. But this, what we have is not that expensive. There could be a collaboration of companies coming together just to, build this as they can. Yeah. So building in large quantities might require, of course, labor, the people, but I'm sure there might be a way of funding this, though it's not.
There is a group in South Africa. I don't think they're on this webinar, but they are building our ventilator in South Africa. So it is not so to the gentleman from Nigeria, it is not a matter of you designing a ventilator anymore if you want to use our design. So it's a matter of building the design, not designing a ventilator, because our design is complete. And that's what Dr. Nystrom went through, which is to show you how to build it.
Yeah, thank you. Yeah, and I'm aware that people in Ethiopia, South Africa are already making use of this design. So a question here says, what's your take on using HMEF filters to prevent cross-contamination when considering a split kit ventilator for multiple patients?
Well, yeah, that's a difficult one. we don't really know about the sharing. So this is putting more than one patient on one ventilator. It was done in New York. I think if you're going to do it because you don't have a choice, then yes, you should put HME filters at the connection to each patient. Because when you share ventilators, especially if the lungs of the patients sharing the ventilators are very different, then it is possible that one patient will exhale into another patient's lungs during exhalation in extreme cases. So therefore, if you put filters where each patient connects to the ventilator, meaning at the Y-piece, then you would filter gas coming from one patient going to another patient if that happens.
Yeah. Okay, so we're planning to round up in 4 minutes. If you have any last minute questions or contributions or anything.
So Eden and Dr. Nystrom, they built a ventilator, and Eden got a lot of experience. So I would say if you're interested in building our design, then reach out to Eden and send him an email. And currently, we're still, the team is still very much focused on getting the FDA clearance so that our ventilator can be used in the United States. But once we clear the FDA, we would be able, to a certain extent, to help people, the people here on this webinar, to address some of the design questions. Like, you know, you could ask, can we use this part instead of the part you have because we don't have that part? Then we could look at it for you and tell you whether this is a good choice or maybe it's not a good choice.
Yeah. So we are hoping that at least we'll have people who take this up and then start building something, help Africa, help your location in whatever capacity that you can. And then if you're maybe a business person, you just want to invest, or you're thinking of business collaborations, yeah, you could also reach out. We could see if we could put you in touch with people who are planning to build. That's also an option. So again, I think I sent my name, website. My website is there. There's a place to contact me if you want to send an email. So yeah, plus so I see that we have a very broad range of audience. So whatever it is that you think you're taking out from this, please share with us on the webinar. Please, Alan, please can we send the link to the survey rather again? I think I can pull it up somewhere here. Yeah, so we have the link to the survey. Please take a minute to fill this. And then if you need the recording of this, it will be available. I think we'll just send it to everyone who registered. We'll send a link to this, and then the website has the PDF, the bill of materials, and the codes are also available. Yeah. Can we get a link to download the content of this webinar? Yeah, I think I sent that earlier on. I'm going to send it again. So you could go to the website. I'm going to send the link again. So that's the link to the CSSALT website. You could just look through the site. But if you have any other specific questions, please feel free to reach out to us. And then we are very, very happy to help. Yeah, I think it's been an awesome time. Thank you so much, except we have some last minute. So thank you, Dr. Sem, for the initiative of starting this building of ventilators. Thank you, Dr. Chaufin, the Director of Center for African Studies, for making us put this together. Thank you, Dr. Nystrom, for being available, and everyone who has worked with us on this. And then those of you who came, thank you for attending. We are hoping that you're going to take this far and wide as much as you can. We really appreciate your presence. Thank you so much.
Thank you so much, and everybody keep safe and let us know if we can help you. Thank you.
Yeah, thank you again for listening. Sorry if any audio quality was horrible, but yeah, the link's posted for hopefully the good version is posted online for anyone to download and watch later. Thanks again for everyone's attention, and feel free to contact me. I pasted my information in the chat just in case for the recording. My email is snystrom11@gmail.com, snystrom11@gmail.com. Thank you again, and everyone take care, stay safe, and good luck making this.